We will continue our discussion of the action potential, starting off with slide 14 here, looking at membrane potential. We talked about this in the previous video. And just remember that all body cells have a separation of positive and negative ion charges across their cell membranes. This separation of charge is called membrane potential. Recall that opposite ion charges attract. So negatively charged ions like chloride ion will be attracted to positively charged ions like calcium ion, potassium ion, sodium ion, magnesium ion, and so on. Therefore, when we separate opposite charges on either side of a membrane, there is the potential to do work when those ions are allowed to come together because they'll be attracted to one another. Be aware, however, that when we talk about a slight difference in charge across a membrane, a cell membrane, it's only over a very thin layer on either side of the membrane, because overall body cells are neutral, as well as the interstitial fluid. There are equal numbers of positive and negative ions in each space. However, it's just a thin layer of negative charge that is formed in body cells and on the inside, and a thin layer of positive charge on the outside. So overall the cell is neutral, but we see near the surface this slight difference in charge. And the only cells that we see able to change that membrane potential is in nerve and muscle cells. So we say that these cells are excitable, which means they can change that ion distribution from being slightly negative on the inside to slightly positive on the outside. They can change that distribution of ions by opening up specially gated channels for specific ions. So the separation of charge that we see between the inside of cells and the outside of cells is due to two things, which we talked about in the previous video, but I'd like to review those. The first one is the sodium-potassium pump. Recall that the sodium-potassium pump distributes sodium and potassium across the membrane against their concentration gradients. So we see 3 sodium being brought out of the cell, and 2 potassium leaving the cell. And this pump contributes about 20% of the resting membrane potential by creating those concentration differences or gradients for sodium and potassium. And this pump is an ATP requiring active transport pump. Again, always transporting 3 sodium out of the cell and 2 potassium ions into the cell. So as a result, we're always going to see a higher concentration for sodium outside the cell and a higher concentration for potassium inside the cell. So if there are channels available for each of these ions to diffuse without energy, we will see that they diffuse from high to low concentration, which for sodium, that would be, if we open up a channel for sodium, that would be into the cell because there's more sodium outside the cell. And for potassium, we would see a net flow of potassium out of the cell. So here we would see sodium flowing in and potassium flowing out with their concentration gradients. The next part of the resting membrane potential, the other 80% of that membrane potential, is due to the differing permeabilities of potassium and sodium. Because the gradient established by the sodium-potassium pump has caused more potassium to build up inside the cell, we will see potassium diffuse out of the cell through leak channels, like we see here in this purple diagram of the potassium channel. That means there's no energy required, and it's simply moving from higher concentration to lesser concentration until it reaches equilibrium. And every ion has an equilibrium potential that's calculated by a special equation that we're not going to get into detail on. But the equilibrium potential for potassium is negative 90 millivolts. So that means there's going to be enough potassium flowing out of here until it reaches a value of negative 90 millivolts inside the cell compared to the outside of the cell. The same thing occurs with sodium. If these doors were open, we would see sodium diffusing into the cell through a leak channel until it reaches its equilibrium potential of positive 60 millivolts. So that means it would become more and more positive inside the cell until that value reached plus 60. And those numbers are calculated using the Nernst equation, which is beyond the scope of this course. So we're just going to accept those values, at their face value. So an important difference to note here, though, is that there are 50 to 100 times more leak channels for potassium than there are for sodium. And we don't see a sodium leak channel on this particular slide, but there are 50 to 100 times more of these channels for potassium than there are for sodium. So as a result, these cells are more leaky to potassium than they are to sodium. So we see a net loss of positive charge from inside the cell through these leaky potassium channels. So those are essentially more doors leading out of the building than there are in. So as a result, you're going to see a net flow of potassium out of the cell, leaving it slightly negative. But what also plays a role is that potassium, as it's leaving the cell, it's drawn back toward the surface because of these negatively charged proteins that are trapped inside the cell that attract potassium back into the cell. So we see a result of this, a buildup of negative charge just inside the cell membrane due to these negatively charged proteins. So as a result of the three influences that we just mentioned, that being the sodium-potassium pump, the membrane being more leaky to potassium than sodium, and the negatively charged proteins building up inside the inner surface of the membrane, that results in this, what we call resting membrane potential. And what that essentially is that there is a difference on the inside of the cell compared to the outside at a different value, being slightly negative on the inside and slightly positive on the outside. If we actually measured this value for nerve cells, it's -70, and for muscle cells, it's -85 to 90. So that means it's more negative by 70 millivolts on the inside compared to the outside. So the difference in millivolts of this charge on either side of the membrane is called the resting membrane potential. So recall that it is in nerve cells the ability to move sodium and potassium through specialized channels that make nerve and muscle cells excitable. Sodium, again, based on our discussion last time, sodium will always diffuse into the cell through specialized channels that open up when a membrane is stimulated, making it more positive inside the cell. So if we look at this graph of the action potential, we see a more positive influx of ions causing the charge inside the cell to become more positive. Then at the top of the graphs, those voltage-gated sodium channels will close. Voltage-gated channels for potassium will open at positive 30 millivolts, and potassium will flow out of the cell through voltage-gated potassium channels. And this continues downward a little lower than the resting membrane potential because these potassium channels, these voltage-gated potassium channels, are slow to close, and we see a little extra leaking out of potassium from the cell, making it a little more negative than resting. But it's okay because at the bottom of this graph we have all voltage-gated sodium and potassium channels closing, and the sodium-potassium pump will redistribute those ions back on either side of the membrane back up to resting potential, and our stimulus can begin again. So what starts this whole process of what we call an action potential are what we call graded potentials. And graded potentials are small changes in permeability that occur at the dendrites or cell body of a neuron. And what happens is some ions are allowed to flow into the cell through specialized channels or through special connections from one nerve cell to another nerve cell, but it allows those channels to open for a particular ion, and that starts the process. Again, if it's sodium ions that are allowed to enter the cell through these specialized channels at the dendrites, those sodium ions will diffuse toward the axon hillock of the neuron and trigger the opening of voltage-gated sodium channels, and that's when the action potential begins. So graded potentials begin when special ion channels for sodium are stimulated to open, and they may be stimulated by a series of events initiated, for example, by touch, temperature, smell, etc. These channels allow some positive charge into the cell, but in order to reach the voltage-gated sodium channels at the axon hillock, a value of -55 millivolts must be reached. We call that value threshold. So once inside the cell, when these positively charged ions at the dendrites flow toward the more negative nearby regions of the cell, those parts become more positive, and that buildup will eventually make its way over a small area, and then the leak channels will and the sodium-potassium pumps will redistribute those ions, and the graded potential goes away. So graded potentials don't spread very far. Here we can see we've stimulated the membrane here. This might be the skin, for example, an axon serving the skin. And we see a little bit of flow of positive charge into the cell, but it's not enough to reach that threshold value of negative 55 millivolts, so those ions just redistribute and it becomes negative inside the cell again, and that graded potential is lost. Graded potentials are very short-lived, and again, they don't spread very far. But if we let enough positive charge in, we will reach that threshold value, and at the axon hillock we'll reach the value of negative 55 and allow an action potential to begin. So again, we looked at this last time. The action potential is shown here in this diagram, and that is when a value of negative 55 is reached. That's what this dashed line means, and that's when voltage-gated sodium channels are triggered to open across the membrane, that spot on the membrane, and all the voltage-gated channels open and sodium comes rushing into the cell, making it positive inside the cell. So we see this sharp increase toward plus 20 millivolts. Then at the top, voltage-gated sodium channels close, voltage-gated potassium channels open, and potassium flows out of the cell through these extra channels until at the very bottom they're initiated to close, because at negative values voltage-gated potassium channels are triggered to close, and then we see the closing of potassium channels at the bottom, and there's no more flow of potassium out of the cell. Then the sodium-potassium pump in this region here of the graph cleans things up, puts everything back on the right side of the cell, and the action potential is over. So when it comes to action potentials, we call its movement in the membrane an all or none principle, which means only if we get enough ion flow into that neuron do we reach threshold, which means the negative 55 millivolts. So we have to have enough positive ion flow into that cell through some stimulus to reach threshold to trigger these voltage-gated sodium channels to open at the axon hillock. So again, these local or graded potentials are occurring out on the cell body and dendrites through special channels that are stimulated to open. Once they reach threshold, once we let enough sodium in, it'll trigger the voltage-gated channels to open, and this is the depolarization we see on the action potential graph. So the reason why we say it's an all or none principle is because if we don't reach threshold, we won't reach an action potential. If we do reach threshold, all the voltage-gated sodium channels in that part of the axon are stimulated to open, and it's kind of like us firing the gun at a horse race. Once the gun fires, that's threshold, all the gates open and sodium comes rushing in. Just like at a horse race, once the gun fires, all the gates open, the horses run out, they run around the track, and you can't stop that race until they come around the other side. The same thing occurs with an action potential. It's an all or none response. So here we can see in the graph, we see this flat part of the graph, sodium channels are beginning to open, but no sodium can flow through because these are voltage activated channels that are only stimulated at threshold. So what is being stimulated, what can be occurring, is those specialized channels out on the dendrites that might be sensory receptors that will open up when stimulated by one of the special senses like light, smells, touch, temperature, things like that out on the skin. So once these channels open, when the cell reaches threshold where we have enough sodium traveling in, we see a depolarization and a steep climb toward positive 30 or positive 20, depending on what source you're looking at. So here we see sodium is traveling into the cell. Then those channels close, and we can see here all the sodium channels are closed. Potassium channels open up at positive values, positive millivolts, and we see a net movement of potassium out of the cell, again making it negative, so it's dropping downward. And then here we see these are slowly closing, so some of little bit of potassium can still leave the cell, but for the most part they're closing, and then the sodium potassium pump, which isn't shown here, is cleaning things up. There's an excellent animation that is worth spending our time watching if it's still active out on YouTube. Sometimes these things do expire, so we'll hope for the best here. Yep, expired. So much for that. It's gone. I'm going to just delete that. So moving on to then a refractory period. The absolute refractory period is a period of time when another action potential cannot be initiated because the gates for sodium are closed and there cannot be any change in permeability to sodium if the gates are closed. So why those gates are closed is because these gates are only for sodium are only able to be opened at the threshold value of -55. So once we reach -55, the sodium channels open at the top, and then they're stimulated to close at +20, and then only potassium channels are open as we rise or fall back down to -70 or 90, depending on the source you look at. So this region here where we have active voltage gated sodium and potassium channels is strictly dependent on the charge inside the membrane. So if we continue to stimulate the membrane, if only the potassium channels are open or only the sodium channels are open, depending on the flow of charge, we cannot stimulate another action potential. So we call this the absolute refractory period that occurs from the beginning of the sodium voltage-gated sodium channels opening to the end of the voltage-gated potassium channels closing, the absolute refractory period, which means we absolutely cannot stimulate another action potential until all the voltage-gated channels are closed again and we're ready to begin stimulating that membrane. After the last potassium channel, voltage-gated potassium channel closes, we could stimulate the membrane, even though we're a little lower than resting, by some extra stimulation of that membrane. So it's called the relative refractory period because it would take a little more stimulation to get enough channels for sodium to open, those special channels out on the dendrites to allow sodium in to get back up to threshold value and start another action potential. So we can get another action potential during the relative refractory period, but we cannot stimulate another action potential during the absolute refractory period. So again, we talked about action potentials being an all or none response. And that means that either you reach threshold and you get an action potential or you don't. In this slide here, they're showing that we have some flow of sodium into the neuron at the dendrites through a stimulus, again like temperature, touch, any stimulus out on the dendrites through a sensory receptor, but it's not enough to reach threshold, so we do not see an action potential. So it just kind of fizzles down. Then if we do have a stimulus that reaches threshold, you can see that we'll get an action potential. Now let's say we give a stimulus that is greater than threshold. We will get an action potential, but if we look, we don't get a taller action potential, we just get more action potentials occurring. So we see we have 3 action potentials occurring when we are higher than threshold. So if we just have enough stimulus to reach threshold, we get 1 action potential. If we have more of a stimulus beyond threshold, we'll get more action potentials. If we have the maximal stimulus, we'll get 5 action potentials we can see here. If I go beyond the maximal stimulus, I'm still going to get 5 action potentials because there is a maximum amount of sodium you can allow into the cell. And that will maximize the number of action potentials you can receive, at that point in the for that axon. So the point is, no matter how much we stimulate the membrane, you're not going to increase the height of this graph here for the action potential. You're just going to increase the frequency. So once we reach threshold, and if we're talking about a stimulus for pressure, for example, so if you're talking about a little bit of pressure on the skin surface versus a lot of pressure on the skin surface, a lot of pressure on the skin surface is going to stimulate more action potentials. So the intensity of a stimulus causes increased intensity of a stimulus causes more action potentials. Not taller action potentials, but just a higher frequency. So if you're talking about a little bit of a pain due to a headache versus a really bad headache with a lot of pain, it's the frequency of action potentials that are being propagated along those axons going from pain receptors in your head to your brain for processing. It's the frequency of action potentials that determines the strength of the stimulus. It's not the height of the action potential, because this can't get any taller. Once we hit plus 20, that stimulates all those voltage-gated sodium channels to close and the voltage-gated potassium channels to open. So this can't get any taller. We can only increase their frequency. And that's a key concept to remember for the test. So again, because of that absolute refractory period, we only see action potentials moving in the direction from the axon hillock to the axon terminals. It's kind of like the wave at a football field. As one person stands up, picture that as a voltage-gated sodium channel. That's going to stimulate the next person standing next to you to stand up, and the next person and the next person. But nothing is actually moving around the stadium. It's simply the opening and closing of ion channels, just like people doing the wave at the stadium. It's just people sitting up and down. There's nothing actually moving across the membrane. And it's the same thing that occurs with the action potential. It's just the change of ion charge across the membrane as it moves down the axon that causes us to conduct information from our fingertip all the way to our brain. So again, it's propagated along the axon just through ion changes and the changing permeability. So in myelinated ions, lipid-containing myelin insulates the ion, forcing ion current to go to the next open area on the axon, which are the nodes of RANVA. So it's at the nodes of RANVA where there's a concentration of voltage-regulated sodium channels. So if we have a myelinated axon, we're going to see a faster transmission because this changing permeability skips over these portions that are myelinated to those bare sections on the axon, which are the nodes of RANVA. So the speed of action potential conduction not only depends on the presence of myelin, but also the thickness of the myelin and the diameter of the axons. Obviously, a thicker diameter of an axon means there's faster propagation, just like we see in a thicker wire. We can see it carries a lot more electricity, a lot more voltage, or current behind that those electrons in a thicker wire versus a thinner wire. So thicker myelin is going to cause faster propagation down the neuron, and larger diameter of the axon will also cause faster movement down the axon. So there's different types of fibers, nerve fibers we see in our body. Type A nerve fibers are very thick, they have a large diameter, and those feed skeletal muscles and sensory receptors. That way we get good response, good communication from the outside to our body, and we can respond quickly. We have type B nerve fibers that are lightly myelinated with medium thickness, and type C nerve fibers that are unmyelinated with small diameter, very low thickness. So those type C fibers are the ones we talked about that might control your endocrine gland secretion or movement through the GI tract, small smooth muscle contraction through the GI tract. We don't want rapid transmission in those cases. So therefore those nerve fibers are unmyelinated with a small diameter. So that concludes our discussion of part 1 of the nervous system. Be sure that you print off the worksheet and answer some of the questions related to some of the topics that were discussed in this video and in the previous videos. So you're making sure you're catching the key concepts and you're preparing for the test.